This is a collection of quantum computing events created and planned by university students and volunteer hosts with support from IBM Quantum. Before we get started, let me walk you through our timeline. We'll be hosting another online session on 29th of October about Introduction to Qiskit. And then we'll be hosting an in-person workshop series where a special guest from IBM who will be joining us to share their insights and experience from the industry. It will happen on 7th of November. At the end of the program, we'll be holding a 5-day hackathon where participants can apply what they've learned and work on real quantum challenges. One notebook will be released each week, beginner, intermediate, and advanced, serving as a self-study module for that week. A short discussion will be conducted every Saturday to review answers and address participants' questions. We'll provide 1 or 2 additional notebooks for absolute beginners who are new to even classical computing. These will cover some of the basic mathematics, classical computing concepts that and all participants will receive an official certificate from IBM Quantum for their active participation in the Qiskit Fall Fest. Eligibility for the certificate will be determined based on participants' engagement in the self-study modules and workshops. And let's begin today's session, Introduction to Quantum Computing. This webinar will explore the fundamentals of quantum computing, providing an overview of its core principles and underlying theories. To guide us through this fascinating topic, we have Viduranga Landers, Qiskit Advocate, who will walk us through the fundamentals and help us understanding how quantum computing is shaping the future of technology. Over to you, Viduranga.
Thank you. Give me a second to share my screen. Is it visible? Okay, so let's start our first session for the Qiskit Fall Fest on quantum computing foundations. I'm Viduranga Landers. I am an undergraduate at UCSC and also a Qiskit Advocate at IBM Quantum. I have been studying quantum computing since about 2020, and I have done research on mainly quantum cryptography and how quantum computing can be applied to space exploration. So let's move on to our today's agenda. So first, we will be looking at how a quantum computer works, and then a little bit on to what technologies and what hardware technologies exist in the quantum computing domain compared to classical computing. Then we will introduce you to Qiskit in a very brief introduction, because we will have another session on Wednesday introducing you thoroughly to Qiskit and programming a quantum computer with Qiskit. I will show you some GUI-based programming of a quantum computer just to give you a good understanding of some of the concepts that I'm explaining. And we will also talk about some challenges in relation to quantum computing and what the future of quantum computing would be. And also I have listed an additional topic. If we have time, we will talk a little bit about quantum cryptography and what post-quantum cryptography means, and some debunking of myths with quantum computing. So before we move on to the session, we'd like to give you some announcements about the Qiskit Fall Fest. That is, we will be having 2 main sessions. This is our first workshop. And then we will have another session introducing you to Qiskit and actually hands-on programming a quantum computer on Wednesday. And then we will have an in-person session on November 7th at UCSC with a guest speaker from IBM. We will announce more details on that. And the registration page is currently closed because some of the logistic details are yet being finalized. And for the rest of the Fall Fest, we have 3 self-study modules for you, which will be distributed 1 per week. And you can go through those modules, learn yourself, and do the hands-on tasks. And we will also have a small Q&A session on every Saturday to reveal the answers for the notebooks and also discuss some of the questions that you may have. Then we will finally have a hackathon, which is more like a research or project-based hackathon rather than doing some random tasks and getting your answers verified. We have a more like a project-based hackathon that will run for 5 days. And for the session, we noticed that some of the registrants are school students, and at least half of the people who registered for these workshops do not have a good background in even classical computing, and they have beginner level Python knowledge. So we will also try to prepare some notebooks for you to get to the speed of quantum computing by learning the fundamentals of classical computing. And also we have tailored the session a little bit towards the beginner side. And I should say that teaching quantum computing within 1.5 hours or 2 hours is not something really feasible. So we will be covering the overview of quantum computing, introducing you to certain concepts and giving you an idea about what quantum computing really is. And then we will provide you some resources for you to learn and all the study modules. And also I should say that some of the concepts that I will be introducing are more simplified, because if you are learning physics and your teacher asked you to consider AR resistance for everything, then you won't be able to learn most of the concepts because you will be doing heavy mathematics related stuff. So similarly, we have simplified certain things. So some parts related to quantum mechanics may not be the 100% accurate things, but it is easier to understand things that way. So with that, I will move on to the session. Bear with me for the first few slides. If you don't understand, especially if you are a beginner, bear with me. We will cover the same things once or twice again, even with this workshop, explaining things one after the other. Okay, so what is exactly quantum computing? Since some of you are beginners to classical computing as well, I think you all know that classical computers, or the computers that we use day to day in our lives, like the laptops, mobile phones, or even microprocessors or Arduino SBCs and stuff, all of those rely on classical bits or zeros and ones. That's how we learn programming, right? We manipulate zeros and ones to achieve a certain task using these devices, but they are so advanced that at our level, we are programming using languages like Python, Java, C. Those are more close to human languages rather than programming on zeros and ones. But maybe in 1940s or the earlier days of classical computing, people used to program these computers by manipulating the zeros and ones and plugging devices, plugging these settings and setting these configurations and all that. So with quantum computing, the main difference is the unit that we use is not a classical bit. So in a classical bit, you have zeros and ones, but in a quantum bit or a qubit, you have still zeros and ones, but you can have a complex linear combination of these zeros and ones, which I will be explaining in the later slides. So this provides us certain advantages because of the methods that we use are the quantum mechanics methods that we use, like superposition and entanglement. Because of these concepts, we can do certain computations, only certain computations, far more efficiently than classical computers. And the thing with quantum computing at this stage is you are basically programming the quantum computers at the gate or qubit level. So if you don't have the understanding of bit level computing for classical computing, it may be a little bit hard, but I think it should be relatively easy to move if you, as we compare it with classical computing as well. So moving on to the next slide, why we are interested in quantum computers. So I mentioned that these devices, since we are using certain quantum mechanic principles or physics principles to do the computations, these can do very specific computations in a much faster and efficient way compared to classical computing. If you know about complexity theory in and time complexity and problem solvability in regular our classical computing, you may have heard NP problems, NP hard, NP complete problems, and categorizations like that. With the invention of quantum computing, we have introduced a newer category called BQP, bounded error quantum polynomial time. That means, let's say, let's take a simple example to explain this, right? So everyone is relying on cryptography for your safe message transfers and all that stuff, right? But you may have heard already that quantum computers are capable of breaking some of these encryption algorithms. The standard for modern classical computing is none of the classical computers, even for the supercomputers, they can't perform the computations that are required to break a single encryption in a reasonable time. But that is due to the algorithms being exponentially time consuming. But with quantum computing, you can have algorithms like Shaw that does these calculations in polynomial times. That is what we put into the BQP category as bounded error quantum polynomial time. I won't go into specific details on that, but what the diagram explains is there are certain problems that are very hard for classical computers, but with quantum computers, you can solve them in a relatively efficient and easier way. But I should say that quantum computers are not going to solve all the hard problems or all the NP hard problems. They are doing specific stuff. And also, these are universal computing devices, if you know what that means. Otherwise, the simpler explanation is it can do anything that a classical computer does, but the thing is, it won't be good at everything it does, right? So keep that in mind. If someone says the quantum computers are going to replace classical computers, that's not going to happen. They can perform the tasks, but they are only good at very specific tasks. Think of it as a kind of a graphical processing unit or a GPU. Okay. So let's go into how the quantum computer works, because now I'm explaining all these BQP and all that stuff, but you may not have an understanding of what a quantum computer is and how it may work. So as I explained earlier, classical computing relies on this classical bit, or you can think of it as a switch or maybe a coin toss, that always have a deterministic state as 0 or 1. It is not going to be 0.5 or 0.7. That is analog computing. There's another domain called analog computing, and it can have fractional values. We are not going to talk about that. The only distinction that I want to make is analog computing is not quantum computing. You may think that when I say quantum bits can have linear combinations of zeros and ones, what that means is not having an intermediate value like 0.6 or 0.7 or something like that. What that means is the quantum bit can stay at both states, both the 0 and 1 states, at certain probability levels, right? So if you have a classical computer, that's like a coin toss. It is going to be either 0 and 1. If it's a quantum bit, it can be, let's say in this example, we can say it is at a 50-50 state of 0 and 1. What that means is, if you have studied A-level quantum mechanics related topics in physics, you may know that there is a concept called quantum superposition, and that allows particles like electrons and other quantum level particles to behave in strange ways. And one of these strange ways is superposition, that allows it to stay in different places or in different states at the same time simultaneously. Okay, so in this case, this qubit is going to be 50% 0 state and 50% 1 state. What that means is, if I prepare maybe 100 qubits, okay, in the same state, and I measure them one by one, as you may all have studied A-level quantum mechanics, I think you may know that a quantum state is very fragile. When you measure it, I will go into details in the next slides as well, but when you measure it, what happens is these fragile states collapse to a classical state like this. So what the 50-50% linear combination means is, if I have 100 qubits prepared at this state, if I measure them, 50% of the time they may fall to the 0 state, and 50% of the time they may fall to 1 state. So the notation here is called the bracket notation. So it is a way of representing a quantum state, and you can safely assume it to be equal to 0 and 1 for the state. So again, some distinctions about classical bits and quantum bits. The top few I mentioned. These classical bits, the thing with classical bits is you can measure them completely, right? It is going to be something like a voltage value, right? So if it's a switch on or off, you are going to measure the voltage, and you can accurately measure the voltage, and you can accurately measure what the state is going to be, whether it is 1 or whether it is 0. But when it comes to quantum bits, qubits, what you can measure is a non-deterministic value. That means whatever the collapsed state that it is going to give you, but you are not going to be able to measure everything about that particle, because due to uncertainty principle, you can't measure multiple things at once. So you are only partially measuring the qubit. And there are some interesting things that are unique to quantum bits, that are first, it cannot be copied and it cannot be erased. So the thing is, there is a theorem called no cloning theorem that derives from the uncertainty principle as well, that states you cannot copy quantum information, because when you measure some quantum state, it is going to collapse. You can't preserve that thing and also measure it at the same time. If you measure it, you are collapsing the state. If not, it is going to be preserved, but you won't know what the state that thing is in. because of that, unlike classical systems, you cannot copy information that are running on a quantum system, or maybe if you are going to quantum key distribution or something like quantum communication, you cannot copy something without collapsing the state or disrupting the state. So now we talked about superposition. So I will explain it further in this slide. So we are here considering a 1 qubit system, where we think we have 1 qubit that can represent these 0 and 1 states, and also the superposition and entanglement features. So I mentioned that we can combine this in a complex linear method. Right? Earlier, the example I took was a 50-50 state. And most of the time, the gates that we have in quantum computing and the gates that you will be using will be to prepare states that are 50-50 in probability. But you can create quantum states that are in this nature with alpha and beta amplitudes. This means whatever the square of the magnitude of that value, because this alpha and beta can be complex numbers, and these are probability amplitudes. That means the square of these two values is going to be equal to 1. So in the earlier stage, we mentioned that we could have 50-50% probabilities, right? But you can't have something like 50-40, okay? Because then what happens to the other 10%? So you are going to prepare 100 qubits, and then 50 is going to get down to 0, and the other 40 is going to go up to 1. And for the other 10%, you are not going to have anything. So that can't happen. That is a physical limitation. And that is also easier when it comes to computations, because you have these conditions and you can properly prepare the mathematical equations for alpha and beta. So now when we add 1 more qubit, or maybe 2 or 3 more, things get interesting. So these systems, unlike the previous one, this previous system could take 2 states at the same time, but nothing more. But in this case, you can have multiple states at the same time, and also there is something called entanglement that we will be looking at in the next slides, that allows you to link some of these qubits in a way that is completely not possible with classical systems. So here what we are focusing is how the state space is expanding when we are adding qubits. So think of it as this way, right? If you have a classical system, and let's say you are representing these classical systems with switches, and you add another switch, let's say you have 4 switches, and you add another switch. So still, you are going to be able to represent 1 state out of 2 to the 32 states, right? So you can have 0, 0, 0, 0, and maybe 1, 0, 1, 1, 1, states like that. But you are going to be able to represent only 1 at one particular time. The thing with quantum computing is, if you have 5 qubits, you can represent all the 2 to the 5 states at the same time. With the examples that we have in the next slides, I will explain this further with a very unique example in quantum computing. So for now, just keep this in mind, but don't think of it as you can, for whatever computation that you are doing, you can take 2 to the n states and reduce everything to a very small number of qubits. This is specifically to represent your states as the inputs. So if you wanted to give maybe 2 to the 5 inputs, or 5-bit inputs in a classical system, you would have to feed 1 by 1 32 times. But in a quantum system, you could technically prepare a state that combines all these 32 states into one quantum state, and then you can put it as an input. And if you properly prepare the quantum circuit, within one execution, you should be able to get your result. So now, earlier we talked about the superposition and how these qubit systems can represent multiple states at the same time. Now, we come to how we are getting the calculations from a quantum computer. So in a classical computer, again, you are measuring a voltage, but that is a very deterministic value, right? It is going to be either 1 and 0, and you can know the bit values for each of the bits. But with a quantum state, you have a qubit, but in a classical state, the input was also a bit, right? It was either 1 and 0 that you inputted, and then you did some process, and then your output was also 1 or 0. But here the thing is, in a quantum system, your input is going to be something like this, maybe 8 states, 16 states, with 4 qubits representing all the states in a superposition manner. And then you do some process, and then at the end, again, you have some complex linear state, but whatever the thing that you measure, for each qubit, you are going to get only one value, right? So if I had the 50-50% superposition for one qubit, when I measure it, which means you can think of it as I look at the value, whether it's 0 and 1, then no matter what the state it is in, it is going to definitely collapse to either 0 or either 1. That is what we have explained here. So now you might think, maybe let's assume I had the 50-50 superposition, okay, and then I measured it only once, and then I get the value of 0. I have another qubit that is at 100% 0 and 0% 1, and I measure this as well. Then also I am getting a 0. Then you may ask, how can you differentiate the superposition state at 50-50% versus the 100% 0? How we do this is we run the circuit multiple times. So here, what we have explained as 1024 shots is we run the same circuit multiple times and get a probabilistic value that is very close to the actual state that it was in. So I hope that you might be getting some insight about how the computation happens now, but we will explore more in the coming slides. So before going into some of the gates and actual working of quantum computers, we need to learn about one more important quantum mechanical principle that is called entanglement. So I mentioned this earlier as well. So the idea of entanglement is you have two qubits, and these two qubits are linked in a way that you cannot explain it in any classical method. You might have heard about this. So let me explain it with the equation here for those who haven't heard about entanglement. So let's imagine the state is this, and I have two qubits, right? So for two qubits, earlier we learned that it could have 4 states like this: alpha 0, alpha 1, alpha 2, alpha 3. But now in our system, what we have is only 2 states. So what happens here is, if you can imagine it, let's imagine I isolate these 2 qubits and measure only the left one, right? Let's assume the left one is correlated to this. And if I measure 0 here, then from this equation, you should be able to infer that the other one should also be 0, because there is no state as 0, 1 or 1, 0 or anything like that. So if I measure one thing, even though I didn't measure the other particle, I know that the other particle is going to collapse to 0 as well. So that is the basic idea of entanglement. So it cannot be explained in a classical way. So this is also known as Einstein's spooky action, and there are some debates about this being instantly happening. But the core idea that we want for here is, when you measure one particle that is entangled with another one, you are effectively changing the state of the other particle as well. So to gain a quantum advantage for any computation, you actually need entanglement. With just superposition, you can't do much. You need entanglement for an algorithm to be really quantum advantageous or have quantum supremacy. So the last quantum mechanics principle that we have to discuss is called quantum interference. This is similar to signal interference. You know that when two sine waves have peaks at the same position, they add up, and when two sine waves have a high peak and low peaks at the same position, they cancel out. So similarly, in quantum states as well, we represent these in wave functions. So if we represent these as waves, and then we can we can create a circuit in a way that has quantum interference that allows us to cancel out certain results and amplify certain values, then that would be advantageous, right? That is exactly what is being done in the Grover search algorithm. So if you know, searching some unstructured data is really time consuming, because you don't know where the specific element that you want to search. Let's say there are 100 random elements and you want to search one. It is not sorted. It is not in any kind of a pattern. So you have to go through everything in the worst case to find the specific element. But what quantum computing does is it creates these states, as I mentioned first, and then it applies certain oracles to create some interference pattern, and it amplifies the specific flag, and it uses disruptive interference to cancel out the other other not relevant results. So that is how we gain a square root n advantage for Grover search algorithm for unstructured data. Okay, I hope you are clear with the concepts up to now. So we will move on to some of the qubit technologies. So right now, if you look at classical computing, it is pretty much on, almost everything is on silicon-based technologies, right? But with quantum computing, there are various technologies. One of the highest sought out technologies is superconducting qubits, which is IBM and Google are using. And then there are also neutral atoms, and also some nitrogen vacancy centers. That means they are using some defects in certain materials to create these qubits. And also there are trapped ion qubits that uses electric fields to trap ions and manipulate them. And for neutral atoms, they are using laser tweaks to trap these neutral atoms and then tweak their states. And also there are some photonic or light-based computing methods and some other methods as well. But the main idea is you have to have some kind of two quantum states to create a qubit. So this is a image that I have taken from the Domain of Science YouTube channel. You can watch some of his quantum map videos as well. So as you can see, a lot of companies are exploring pretty much all these technologies. And there are some other other hardware related companies, and also companies that explore software packages as well. So the state of quantum computing right now is there is no specific technology that is being sought out by every company or every nation or everyone. There are different ways of modeling these quantum systems, and there are certain related mathematical concepts that differ from each other, but most of the time the basic gates and all that are equal in almost all the systems. So this is what a quantum computer looks like from the outside. I will show you an inside one as well. This is one of the IBM's quantum computers. And this is what it actually looks like with some cryogenic coolers and all that stuff. I have, and also you can see some of these server kind of racks. These are the control systems, and these are actually classical systems that are used to control this quantum computer. So here we have a nice diagram explaining all the parts and some of the temperatures that are being used in superconducting computers specifically. So if you can see it at this stage, it is at 4 Kelvin, and at this stage it is at 800 millikelvins. At this stage it goes down to 100 millikelvins, and finally at the near the processor level it goes down to 15 millikelvins. So to compare this to something that makes sense, space is only about 1 or 2 kelvins, but this is going down to 15 millikelvins, and it is almost like the coldest thing that humans have ever made. And this is what a superconducting system looks like, with several qubits, and there are resonators and the other control mechanisms. So the rest of the stuff are mainly for controlling the qubits and measuring the qubits, and also mainly the cryogenic related like cooling systems and other refrigerator related stuff. The reason why this needs to be refrigerated or go down to 15 millikelvins is these quantum systems are very fragile, and even the slightest temperature change, or maybe cosmic rays or any other radiation or even noise or something can have a huge impact on that. So you have to like safeguard these and go down to millikelvin level temperatures. So this is again another system that IBM has with all the controls, hardware and all that. And this is one of their recent processors. They have more. They have processors with more qubits than this, but they have gone to different layered structures with qubits and control hardware, and these are being designed on silicon wafers. So the advantage with superconducting qubits is we already know a lot about managing silicon, because we have fabs for our classical computers, and we can use some of the same technologies to develop these as well. Okay, so let's move on to what is Qiskit. But I should say I will be giving you a very short introduction, because on Wednesday we will have a lengthy workshop with some hands-on exercises as well. But I just wanted to give you some basic idea of what Qiskit is. So Qiskit is actually the quantum programming language that we are using to program IBM's quantum computers. So how you can program a quantum computing device today is in a process similar to this. So you are the user, and then you have a cloud service that enables you to access these services, and via the cloud service you connect to a server in their laboratory, and as I showed in the earlier ones, the control circuits. You connect to the control electronics, and the control electronics will manipulate the quantum processor, measure the qubits, and get the results for you, and then go back through the process and give you the job results. So that is the basic flow of you submitting a quantum program to actual hardware and getting the result back. So I hope most of you have heard about the scikit library, like the scikit mainly that is being used for ML and tasks. Similarly, Qiskit is a Python-based SDK mainly, and it is the quantum information science kit. So that is what goes as Qiskit, and this has been in development for many years, and in the recent years the latest version is 2.0, which is a stable version. And you have the Qiskit runtime and the Qiskit ecosystem that has a lot of applications that are being currently explored, and some of the applications that are being currently used with industry partners, and also some free tier cloud access to quantum computers. So the pattern with Qiskit, or you can think of it as similar in almost all the quantum computing platforms, is if first you should have a problem that you are going to solve, right? So what we do with classical computing is when you have a problem, you maybe start looking at data structures or maybe the algorithmic perspectives of solving that problem, and then you basically code that algorithm and input whatever data you have, and then you get the output. But with quantum algorithms or quantum computing, you have to go down to certain layers, because first of all, especially if it's a new problem, you should find a way to map the problem into quantum circuits and operators. So right now there are lots of problems that are already mapped into quantum circuits and operators. So there are ways that physicists and mathematicians has explored and solidified ways of implementing solutions to certain problems. But if your problem is new, you have to map it to the quantum computing model first, and then you create that quantum circuit. So here, by mapping, what we are meaning is basically creating that circuit after the mapping process is done. And then for each of these quantum hardware, there are certain limitations. So some of the qubits may be capable of entanglement, but as you can imagine, these qubits needs to be placed in a flat surface, and almost all the qubits cannot connect to each other, right? So you can't have connection links from each qubit to the other one. So most of the time, the qubits are connected to their neighbors. So it is not possible to entangle whatever qubit you want. So what happens is, during the optimization process, the transpiler will identify the necessary structure for your program and the hardware, and then it will map your program to the specific hardware by maybe adding some more gates, removing some gates, and maybe changing the entire layout of the program. I will show you an example for that as well. And then once this transpilation is done, it will go to the Qiskit runtime, and it will be executed, and then the results will be given back to you. So in the free tier and also even in the pro or paid tiers, you have to wait for a quantum instance. So let's say there are a very limited number of quantum computers, and there are job queues for that. So when you submit a job, it goes to the queue and it waits there. And once it is processed, you get the result back. And then once you have the result back, you can do the post processing. All right. So is everyone good so far? All right. Thank you. Okay. So now we are going to look at how we can program these quantum computers. So earlier I mentioned that these are being programmed at bit or qubit level with gates. So these are some of the example gates, right? This Hadamard gate is the one that we use to create superposition, the state that I mentioned as 50-50. And we have some classical similar gates, just the X gate or the NOT gate, which swaps the bit from 0 to 1, or if it's in 1, it swaps to 0. And then we have some other phase related gates, like I said, ST and some of their inverse gates. So if you are working on a simulator, this means basically applying some linear algebra matrices. So I will show you some of the examples in the ones, but to explain what the diagram means is these are the qubits. So this is qubit 0 and this is qubit 1. And this measure and 2 means we are measuring these qubits and storing their values in classical bit 0 and classical bit 1. And time flows in this direction. So that means you apply the H gate, Hadamard gate first, and then you apply a C0 gate. This is a barrier to you can think of it as a block for the program. So you separate that part of the circuit from the rest. And then we have the measurement gates. Okay. So you don't have to study this or remember all these metrics data, but if you are doing that mapping process of a problem to the quantum computing model, then you may need the knowledge of the linear algebra and matrix processes. But to do certain tasks and to explore, you may not need all the knowledge about these matrix multiplications and the linear algebra stuff. But this is to give you an overview of how quantum gates differ from classical gates. So in classical, what you have is most of the time you have multiple inputs and you have single output. But in quantum gates, it is called universal unitary gates. So these gates should be reversible. So for example, you can't have an AND gate because for all these zeros, you don't know what the starting state was. If I get zero as the output, I can't say about its previous state, whether it was both the inputs 0, 0 or 1 was 1. So in quantum computing, what should happen is you should be able to tell about the previous state given the output state and the gate you applied. So that is why we use these linear algebra matrices. And these are some of the gates, and these are 2 qubit gates. So I will explain them later on. And this is one of the 3 qubit gates that are there. So yeah, again, talking about classical computing, this is what you do with classical circuits, right? So you have multiple inputs, you add some gates and you get these outputs. And most of the time, most of these gates, whether it's AND or not, they are going to give you one output for multiple inputs. So it's a totally different paradigm from quantum computing. And some technical things are that you are working with bit vectors. That means you are working with vectors, but they are always zeros and ones. They are not going to have complex values for the vector or any probabilistic values. And also you are relying on Boolean algebra. That means whatever the calculations that you are doing are primarily based on zeros and ones. And also, as I mentioned in the previous slide, there is no no restrictions for copying. You can have some methods to copy the values with flip-flops and all that stuff. And there are universal gate types. I'm not going to explain all these for the beginners. If you don't know that, just search about it later on, or just forget about it. It is not that relevant. And yeah, if you today wanted to build a classical circuit, you could maybe use some transistors and build them up yourself, or maybe you can design a PCB and get it manufactured from someone else. And there are like macroscopic level technologies that allows you to build these things. But in quantum circuits, that is not possible. You need to have the capability to manipulate quantum states. So these are very fragile systems. And the main difference from this to this is the qubit is going to stay as it is, right? It is not going to add channels, reduce channels, and all that stuff. It is going to stay as it is, and you will apply the gates or gate blocks onto those qubits. So you start with some number of qubits, and you end with some number of the same number of qubit results. So moving on to the next slide. So for a single qubit, how we represent its state is mainly using a blood sphere for the visualization purposes, because for a single qubit, you can manipulate it in three kind of ways, right? So earlier we talked about these alpha beta states. So alpha refers to the cos theta over 2 in this blood sphere. So if you have a certain intermediate state, so this is basically 0, this is 1. So any intermediate state or rotation or anything like that adheres to these two equations. So it is easier for us to visualize and also do the linear algebraic calculations. So when we are taking the probability, or if we have a random state like this side, and we want to measure how probabilistic it is to get 0, it is going to be cos squared theta over 2. And for 1, it will be again a complex equation. And the interesting part is, since this blood sphere is with the unit vector 1, it is always going to sum up to 1, because this is a probabilistic state that we are measuring. And some of the qubit gates that we explored earlier are shown here as well. I will not go into details of all these stuff, but when we provide you the slides, you can maybe refer to these, because these are the alpha beta states, and how these gates manipulate these states. That is what is shown here. And this is some of the representations that we use in Qiskit. So this is just to give you an overview of what it looks like at the gate level mathematics. But we are not going to dive deep into that. And sorry, my mistake. This is not 1 qubit gates. It should be 2 qubit gates. So we have a set of 2 qubit gates here. For example, if I take the CX gate, which means controlled node, what happens is it is taking this as the control qubit and this as the target qubit. That means if the control qubit is 1, then only I am going to apply the NOT gate to the target qubit. So this is the core part of entanglement. So without CX gates, you can't have any quantum advantage. And there are some other controlled Z rotation gates that are like, so X gate means basically rotating it around this. and around the other axes are the Z and Y gates. So similar to that, the control C means rotating it around the Z axis. So one more slide, two more slides before the demonstrations. These are called Bell states, which means there are 4 ways to create equal entanglement, equal superposition entanglements. And these are called the Bell states. So these are the 4 ways or 4 gates of creating them. There is no point of diving into all the mathematics because most of you are beginners. So I will quickly go to the demonstration now, a small demonstration to give you some intuition on what is happening when we are applying these gates. I hope this is visible. Okay, so this is the Bloch sphere representation that we talked about earlier. And these are the alpha and beta values that we have. Okay, and you can think of it as the probability as well. Now, I'm starting with 0 state. Let's say I want to apply the X gate or the NOT gate. Now, it changed from 1, 0 to 1. And now, if I want to apply Y gate, again, the same thing happens. But you can't see what is exactly happening with the Y gate. And for Z, nothing happens. Right? Now, let's look at the H gate. This is what I told as creating the equal superposition. So you see, now it is in between 0 and 1. So what happens during a measurement is we measure on one axis. So let's say I am measuring on this axis only. So if it is in the middle of it, then it is definitely going to have to collapse to either this side or the other side. So that's you can think of it as the simple idea of measurement. If it's in the middle, it has to go to one of these edges, right? And let's look at some of the rotation gates. So this means these gates means this is a 5/2 rotation, but this is going to rotate it by a small angle. So you can see the visualization better. So see, now this one is rotating around the x-axis. So if you have the negative angles, it is going to go to 0. Similarly, this y1 is going to rotate around the y-axis, and the z1 around the z-axis. So we are using this to compute things more efficiently than classical computing. That is the basic idea of quantum computing. So moving back to my slides. Okay, so I earlier explained how the quantum computing happens. So this is the idea. You prepare multiple states at the same time. Okay, superposition of all the possibilities. So let's say you wanted to input multiple inputs. Now you created a one single state that represents all the possible inputs, and then you input it. So this is not a Bloch sphere actually. This is something called Qisphere that is mainly used by IBM, and it has some other way of representing these multiple qubit states. For now, just think of it as something that allows you to represent all these multiple qubits on a sphere-like structure, right? So all these ones are different states that you can have with 4 qubits. So you created a superposition of all these probabilities with all these H gates, and then you applied some oracle here, or let's say this part is the creation of this state, because you start with all zeros and you have to somehow create this superposition. So this is the part that creates it, and this is your computation. And then this again collapses the previous ones and with interference patterns. And then you finally get the measurements. And when you get the final measurements, you get one result. I will explain this algorithm so you will have a better understanding. Okay, so this algorithm that we have implemented here relates to one of the first quantum supremacy demonstrations. So, or you can call it an algorithm that could perform better on a quantum computer compared to a classical computer. One of the first such algorithms discovered was the Dutch-Josa problem. So ignore the complex mathematics part. This is a very simple idea. Okay, so imagine this as an oracle, or maybe imagine whatever. You have a black box, right? So you can give an input to this black box and it will give you an output, right? The input could be multiple bits and the output will always be 1 bit. So what Dutch-Josa says is you are given a guarantee that this box will either have a constant function or a balanced function. So what does he mean by a constant function? A constant function is something that gives either 0 for all the inputs or give 1 for all the inputs. That means it doesn't matter what you input, it is always going to give 0, or if not, it is always going to give you 1. And then what is meant by balance is half the time, for half of the inputs, it is going to give 0, and for half of the inputs, it is going to give 1. So the question is, how many times you should run this oracle or query this oracle to identify whether the embedded function is balanced or constant. Okay, so that is the simplest idea. So if you know a little bit about classical computing, you can definitely come up with the answer. That is, if you have n inputs, then you definitely have to have n over 2 plus 1 inputs to determine, because let's say I have 100 inputs and Dutch-Josa says for half of the time it is going to give 0 and 1 for balance. That means for 50 it is going to give 0, for 50 it is going to give 1 if the function is balanced. But in the other case, it is going to give 100 zeros or maybe 100 ones. You don't know whether it is going to be 0 or 1 in the constant case. So in this case, let's say I am going to query the oracle with certain inputs. So I start with my first input and move on, and I get a 0. For the second input, I'm getting a 0. For the third input also, I'm getting a 0. Still, I can't be sure whether it is constant or balanced until I input 51 values. If I am constantly getting zeros, once I have input 50 values, for the 51 value, for the 51st input, if it is balanced, it should definitely give 1 because it has already given 50 zeros. So that is the case for Dutch-Josa problem. If you are doing a classical computation, if your n is something like 1 million, you have to run it at least 500,000 plus 1 times. Now, what quantum computing does is, if you have enough qubits, it creates all these states at once, just as in this case, and it runs a single query and it gives you the output. So a similar problem is the Bernstein-Wasserani. This is a special case of Dutch-Josa. It is looking at what the actual, so it is looking at a function of the type where you have an input and you take the modular addition with a certain string. So let's say you have 100, 10100, and you have a string 101. Then what is your modular addition to that? That means XOR between these two values. So it is going to be 001, right? So in that case, what Bernstein-Wasserani asks is how many times you should query the oracle to find out what the string it has embedded is. So it's a special case of that JSA. So here, this circuit implements both of these. So let me show you it with an actual implementation. So yeah, this is an implementation that has a string 1101. I hope that you can remember that and keep that in mind. So I will show you the entire process that I explained to you with this inspect feature. So again, to explain this circuit, this is just some reset values that I am using just to make sure that all the values are starting with 0. And then this is a barrier, as I mentioned, a block that is used to separate certain gates from the other parts. And this is a NOT gate that is specific to this particular algorithm. And this part is what creates the superposition. So let's have a look at it. So first step, no problem. I am still at all 0 state. And now I am moving to the barrier. No issues with that. Now I am applying a NOT gate to the leftmost qubit, and now I have 1 0 0 0 0. So that's just something specific to this algorithm. You have to make the ancilla qubit or the calculation qubit in a certain state, and then I am moving to the superposition creation. Now you can see this state that had 100% probability has been distributed to all the states. Now this one, so I am giving the input. This state is what I am giving as the input. So these red and blue markers are certain phase values that are associated with like the Z rotations and Y rotations. So it is something specific to the algorithm. So you don't have to worry about that. You need this phase to create the proper interference pattern and get the final result. So that is why we are doing that. And now we move on to the string matching pattern, right? So this is the last one. So we had 1101. So this is the least significant bit. And I am applying a gate. This entire part, you can think of it as the entire oracle. Okay. So this is the oracle that I am querying. So unless you are given this, let's say now in this case, I build the oracle, but most of the time you won't know what this oracle is. So your computation should give you the result that you have implemented here. That means even if I didn't see this part, I should be able to get the result as 1101. Otherwise, there is no point of having this algorithm. And now I apply the Hadamard gates again for only the input qubits, because I am looking at 4-qubit, a 4-bit state here, but I added another qubit just to do some computation related stuff. And then I added superposition gates or Hadamard gates to only the input qubits to create the interference pattern I need. And then what I have here is these states. So since this qubit is still in a superposition state, I am getting 0 1101 and 1 1101. But when I measure all these qubits, I'm going to get 1101. So as you can see, even if I didn't know these 3 qubits, I am still getting the result by giving all zeros and creating a superposition. And just with one execution, I'm able to get this. You don't have to execute this for 1024 shots. In this case specifically, you are going to get it with one shot, which would have taken you at least 9 shots in a classical computer. And you can think of it what happens when it increases from the size. So this is the Qiskit code for this. Lisita will go through this on the Wednesday session, and I will show you an execution of this on an actual quantum hardware to explain you some other things that I'm going to cover. So as you can see, this is basically runtime usage, including control hardware. It doesn't take this much of time to run on the quantum device. So you can see now in our previous graph, we only had 100% probability for this 1101, but here we have some 1111 and some other values as well. Now this is actually pretty good compared to what we had maybe 3-4 years ago, because back then, if you execute even a simpler algorithm like this, it is going to have a lot of values here. But now the devices themselves are somewhat fault tolerant, and if you add some error mitigation methods to this protocol, this is just the raw vanilla implementation of the Dutch algorithm. But if you add some error corrections, then you can remove all these parts and get the final result. But even in this case, you can get the highest value and take this as the result, which is much more computationally efficient compared to the classical one. So remember I talked about some of the transpilation processes and having some universal gates and all that. So this is the actual circuit that was run on the hardware, which is not what I submitted, because it has decomposed my H gates to some other gates, and it has identified that it can't find some qubits that could be entangled in the way I provided, like this. So it came up with a number of qubits that would be required to create this specific entangled state. So as you can see, my 0th qubit is actually here, my first qubit is here, second one is here, and third one is here. This is my 5th one. It's in the middle, the angina. Okay, so and how you submit a job to this is so earlier I did this. I have 2 instances. Somehow this one is paused. So this has 127 qubits and this has 133 qubits. And as you can see, there are like thousands of or hundreds of jobs pending for each of these devices. And it usually takes at least several minutes, so maybe an hour or 2 to get a result from that. So going back to the slides. Is everyone following what I have been explaining so far? Or do you want me to explain anything further? Okay. Okay, now we are reaching the final stages. So some of the challenges that we have, as I mentioned, is mainly with noise and error. So what we mean by quantum decoherence is, as you know, even in classical systems, like you have the pendulum swinging, it will reduce its energy due to air friction or something. And similarly, these quantum states are also, due to noise and other environmental factors, going to reduce their energy and collapse into much more simpler states. So that is what is simply explained as quantum decoherence. Whatever the states that you have are going to change with time. So at this moment, it is at some millisecond levels or microsecond levels for most of the computers. But even with that, you can compute a lot. The thing that gets impacted with the quantum decoherence is mainly how much depth you can have for a single circuit. So the longer your circuit is, the more time it takes to run on an actual device, because all these get appended one after the other. And yeah, there are some noises related to how the gates are applied. So these gates are being applied as waves, microwaves. So there may be some errors in applying those signals, and it may be change the rotation values by a higher amount or a lesser amount. And there could be environmental factors. Also, as I mentioned earlier, even if I put the 0 reset gate, there could be errors with the reset gates as well. So maybe the state started with some smaller random value, not exactly 0. So those errors are there. And what we have as a solution is, first thing is quantum error mitigation. This is basically identifying errors unique to the systems, and then applying certain post-processing methods to reduce the noise. And there are certain methods that are relevant to this. But as you can see from the example, without any mitigation versus with zero noise extrapolation method, you can have much correct values or much sophisticated values, rather than having some random values being shown in the graphs. So now, when it comes to the quantum utility part, what quantum utility means is what you can actually do with quantum computing right now. So these devices are noisy, but I can assure you that many companies, even including airlines, automotive companies like BMW, and financial portfolio companies, and you have heard about HSBC getting into a partnership with IBM, and all these companies, even NASA have actually performed some optimization tasks with their DSN scheduling or their antenna scheduling. So these tasks can be performed even with these noisy systems once you applied quantum error correction, and they are way efficient than classical computers, even at this stage. So the quantum advantage is basically a term, or sometimes it is called quantum supremacy, is when your device can actually run something, your quantum device can actually run something that is either cost efficiently or time-wise efficiently compared to a classical computer. And there have been a lot of demonstrations, like the Dutch algorithm and all that stuff. They have been demonstrated way back in 2010s. But most recently, both IBM in 2023 and 2025, like a couple days ago, Google Willow processor executed certain material property related calculations that are actually relevant problems for today's world, not some specific problems that were crafted to be efficient on quantum computers, but are actual problems that are being run on classical computers that were run fast on quantum computers. So again, back to error part. The final frontier with this is with quantum error correction. So error mitigation is something else, which is post-processing your results in the noisy systems. And we can do some utility level tasks even with that post-processing methods. And where quantum error correction comes is you combine multiple qubits to create a logical qubit. So if you are following the mainstream media or news about quantum computing, you may have heard the concept of logical qubits, and now people are talking about scaling in logical qubits. They are not talking about how many qubits you have in a specific chip. What they want to know is how many logical qubits you can have. Maybe you are using 4 qubits to represent one single qubit that is fully error corrected. This is not something very unique to quantum computing. If you know about classical computing, in critical systems, we have like triple modular redundancy. You use 3 of the same systems to get a single value. And you also have, even with ASCII, initially the 8-bit was a parity bit. So it was basically for error checking and error identification. And there are lots of error correction that are happening on classical computing, even without your knowledge. So similar things have been developed for quantum computers as well. The only thing is quantum error correction initially is a little bit costly, because you need multiple qubits to simulate or to create one logical qubit. Not simulate, to create one logical qubit. So it is costly at first, but the best way for scaling is quantum error correction. So with those things, we can move on to the future of quantum computing. So there are certain reasons why we are doing this. I will explain in the coming slides as well. So quantum computing is not just something theoretical limited to physics or limited to mathematics. It is something that have been utilized in the real world, and that is being currently utilized in the real world. So there are a lot of developments related to quantum computing. So there are certain opportunities related to developing the quantum processors, hardware, and also a lot of opportunities in developing these quantum algorithms and actually mapping these problems to quantum circuits, more and more problems, and also creating the software and middleware related stuff. And also the latest one is with quantum machine learning and related quantum AI concepts. You can treat a quantum computer as a sort of a GPU, or a graphical processing unit, or an accelerator that could accelerate your AI or ML tasks. And with that, we are moving to an era of quantum HPC, or quantum high performance computing with quantum accelerators. So that is the current and the most latest advancements in quantum computing. And you can think of the domains that are relevant to yours with the future of quantum computing as we have shared. So before diving into the exact companies and stuff that they are working on, I will quickly introduce quantum cryptography, because I think if you are working in the software domain, and if you join the session just to look at what quantum computing is, and because of the hype of quantum computing being able to break cryptography, then you may be interested in this. So am I audible? Sorry, my network suddenly stopped. Am I still audible? Okay, thank you. So I will quickly go through this. So the basic idea, if you don't know what classical cryptography is, there are 2 main concepts in classical cryptography. First one is symmetric key cryptography, which means think of it as you wanted to send some document to a friend, and you both met maybe a month ago and discussed some and shared some key for how the encryption process would happen, and then you send and maybe a letter by encrypting using that key, and then you will send it on regular post, or maybe on ask someone else to deliver that, so you don't mind them looking at it because you have encrypted it with one key, and the other person knows the exact same key to decrypt it. So basically the keys that both the encryptor and the decryptor have is same. The main problem with this is how you distribute the keys. So I mean, if you haven't met the other person, how you are going to share the same key for that person? So that's a big problem, right? And when it comes to that's why we have asymmetric key cryptography, which is more like RSA and stuff, that is highly vulnerable to quantum computing. Is you have certain mathematical models that allows you to create a key on your end and distribute it in a way so with another key, so that the person on the other end can use a different key to decrypt your message. And if he or she wants to send a message to you, he will use his public key, and he will use his private key, and the other person can use his public key to decrypt, or vice versa. So this is mainly relying on modular arithmetic and prime numbers. So that is where quantum computers come in, because with the invention of Shor's algorithm, you can factorize numbers way faster than, or in polynomial time, compared to classical computers. Classical computers, it's exponential, but in quantum computers, it is a polynomial time algorithm. The only difference is in how fast your quantum computer is, and in certain operations, and how error corrected your quantum computer is. So as you can see, if you have the enough number of qubits that are logical, and if you have a fast enough operation of megahertz level, then you can easily crack these RSA or any other algorithms with quantum computers. So that's the basic idea. And also with Grover's search algorithm, what I mentioned for unstructured searching, it reduces the algorithm down to square root of n. That means even less than polynomial time. So with that, again, the symmetric keys are also vulnerable to a certain extent, but that could be avoided with by increasing the number of keys. And there have been certain regulations and some inventions taken place to avoid this. So you don't have to go to a completely new paradigm. NIST has given some protocols like Kyber, Dilithium, and some other protocols. If you are into cryptography stuff, these protocols are currently safe from quantum computing. Currently, that's also why this new concept has emerged as crypto agility. That means your applications should be independent from your cryptographic protocol, because if tomorrow someone finds a way to break that thing even with a classical or quantum computer, you should be able to quickly change the cryptographic protocol and go with another one. So that's why I pasted it here in case you are into developing and stuff. So another thing that quantum computing or quantum communication allows is it actually allows you to distribute these symmetric keys so that you can have a fully secure communication. So the idea is you can have a one-time pad, or you can encrypt bit per bit using a password or a key that is the same length as the message that you are sending. If you have a symmetric key, that is called a one-time pad, and it is the most secure, or it is a fundamentally secure one that you can't break. But this cannot happen with our current technologies, because there is no way to send a key safely to a person in the other side of the world. But with quantum key distribution, you can actually do that. So what this does is, you again use qubits that are put in certain states, and then you measure these in different axes. These are at random, and using one quantum channel and one classical channel, you can distribute these keys without them being exposed to any EF. So let's say now, let's not go into details of the mathematics, but just think of it as some way that we can use a quantum channel to distribute a secret key. The key point here is, let's say I am tapping into the quantum channel and I am trying to observe what Alice and Bob is passing between. Since this is a quantum channel, if I measure the qubit that is being passed, that is going to get collapsed, and Alice or Bob is going to get a different result. So here what it shows is, Alice has decided what the key should be, okay, and she is sending this by encoding it in a certain basis. So let's say now here, Alice's horizontal basis is 0 and vertical one is 1, and these diagonals are 0 and 1 for Bob. Now Alice is sending this in a certain way according to her understanding, and then Bob is measuring them in a different basis randomly. This is not anyway correlated to this. So at the end, Bob is getting certain results, and finally what they do is, Bob will tell what the measurements he did. So Alice knows which numbers that matched the bases that she set. So they can remove all the bases that didn't match. So this one is sent in this state and this direction, and Bob has measured it in the diagonal direction, so they have to discard it. So similarly, this one is in this direction, but due to some noise or something, that bit didn't arrive. So end of the day, if some Eve interfered in between, all of these bits are going to get incorrect because the states have collapsed. So that's the basic idea of quantum key distribution, which is an added advantage with quantum information. So moving on to the last part, some myths versus reality. I think I covered most of these. So first thing is, quantum computing industry is not something that is like all simulators, no hardware, or something that is being only explored in academia or something like that. If you look at the names, Microsoft, Google, Intel, and IBM, and all the big companies have invested millions, if not billions of dollars, and the current market value is about $55 billion, the total investments in the entire world. So there is a huge gap in quantum computing professionals or qualified professionals in the entire world. So India last year invested, I think, 5 crores of their money into developing quantum computing programs in their universities. So we plan to do this with the IBM partnership for the Qiskit Fall Fest, because we also wanted to introduce quantum computing to Sri Lanka. So I will definitely suggest you to if you are interested, this is a little bit of hard field because most of the current qualified people are with masters or PhD degrees. But it doesn't matter. You can start at high school level. I started at high school level with some of the online courses, and I know a lot of people who started at school level or undergraduate level. It's just understanding the math, and also if you are not into math, because things have evolved a lot in the recent years. Nowadays, you don't have to go deep into the math. You can touch a little bit of math and also look at the higher level of implementing these things. So maybe working on the hardware related or other software stack related stuff. So yeah, I wanted to like give you a suggestion that you should not think like this. You are not born too early to work on quantum computers. You are born just in time to work on quantum computers, because why slave to an AI when you can work on the coolest thing in the world, right? It's literally the coolest thing in the world. So just to give you some resources, we will provide this slide set. These first few ones are mostly IBM related ones, and these are really good resources. But if you are doing some self-study using maybe, let's say, 2020 or 2021 kind of materials, then keep in mind that the Qiskit platform has evolved a lot. So a code segment that you may see on some 2020 or maybe even up to 2022 or 2023, they won't work in the current framework. You might have to install an earlier version if you want to run that exact thing. But the AI tools are also somewhat good. I won't say good, somewhat okay with programming in these quantum computing languages. So maybe you can try to use them to convert them, and especially if you are doing it at the basic level, then definitely you can learn a lot using the AI tools. And yeah, all these are suggested for you to study if you want to get into quantum computing. And also IBM Quantum has recently launched an entire platform with free courses and some badge systems and credly badges and all that. So these are very detailed ones with YouTube videos, notebooks, and all that. So yeah, definitely check those out. And that concludes my session. So if you guys have any questions, we can ask them. So I'm looking at the chat. So the first question we have is why these two shows? Yeah, the in-person workshop is currently closed, as I mentioned, because we are yet to finalize some logistics, especially regarding the speaker. Is there any WhatsApp group? We haven't created the WhatsApp group, but if you guys prefer, maybe we can do. But we send all the announcements via emails as well. We had a small mistake in just posting stuff on our social media, but we are updating all the important announcements on our Luma page, so you will get an email notification once that is updated. Is there any other questions that you wanted to ask related to the session, or maybe some suggestions? Yes, sure. I will send the PowerPoint. Certificate of participation. Yes. So currently, what we have decided is we have only 2 workshops. This one and the Wednesday one. Then the in-person workshop is run separately. But we have 3 self-study modules that is actually provided by IBM. And the first module is a beginner one, and there is another intermediate and advanced module covering some of the key applications and how you can run these quantum computing programs and to get some hands-on experience. So we will create a way to submit these notebooks so that we can evaluate whether you attempted them genuinely, and then we will give you the certificates. Do we get a recording of this meeting? Dhananjay, I think we can provide, right?
Yes, we can, right?
How can we obtain the probability by squaring the coefficient? How does that work? Okay. So the basic idea is, let's say now this is a linear system, right? So if I give me a second. So what is shown as 0 is actually this with alpha plus this with beta, right? So when you want to calculate this is a coefficient of a linear system. So when you want to calculate the probability of this system, so you have to get the square of the coefficient, square of the magnitude of the coefficient, and these values are actually adhering to this. So I don't remember the exact principle what this is called. Sorry for that. But there is a specific principle in linear algebra that says that it should adhere to this. So you can think of it as, not exactly linear algebra, but related to this, because we are specifically saying that alpha and beta squared are probability values. So these should be 1. So this is a given statement for our equation. So if you have multiple values, let's say you have 1 0 0 0 and maybe 0 1 0 0 and so on, then you might have alpha, beta, gamma, and delta, let's say. So when you have that, what we are saying is all the coefficients, magnitudes, squares should sum up to 1, because I think that's something related to probability. Yeah, it comes from probability. I'm sorry, I can't derive it right now. But if you search for it, you should be able to find the derivation of it. It is accurate, It's not something that I came up with. And it has a simple derivation, but I can't remember it right now. I will send you a resource if you can drop me a message. Sorry about me. Okay. So yeah, if you guys have no more questions, we can wind up the session with the photograph. Oh, sorry, that's not the question. Yes, they are connected to the series. So we have decided not to distribute the first one yet because we haven't covered the Qiskit module, the Qiskit workshop. So on Wednesday, we will distribute the first notebook set. You can run it on Collab, or maybe there is another platform called QBread, free. You can run it on them, or you can run it locally. And they have certain tasks for you to do and certain topics for you to explore. Especially the first one covers how you apply those gates, what I did with the GUI, how to write a program for that, and how to add measurement gates and how to get the results, how to draw those. Like I used the GUI for you to show, but the self-study module 1 contains all the necessary things for you to actually run a program on a quantum hardware. And Lisita will also guide you through this with some hands-on examples on Wednesday. So yeah, we before the Saturday sessions, we are thinking of getting your submissions. But if you guys prefer, we can move the Saturday Q&A session to Sunday and allow you guys to work on the self-study module till maybe Sunday evening. So we will have the final deadlines for self-study module submissions on Sunday evening. If not, the current schedule that we have planned is for you to submit the self-study modules by Saturday evening. Shall we send a call via email or other communication method to get this? Or like, is there anyone who prefers Sunday at this meeting? Otherwise, we will stick with the current schedule. The modules are connected to the series. They are provided by IBM. So, I mean, you can learn a lot by doing them. So we just want to know who participated in it. You don't have to get everything right, but you just have to genuinely attempt to do it. If there's anyone who prefers to switch it to Sunday, or if you need one more day to work on it, especially because it's weekend, can you maybe put a thumbs up or something? Otherwise, we will keep the regular schedule for Saturday. Okay, there's one person. 2, 3, 4, 5, 6. Okay. 7. Okay. 8 and more. Okay. So you guys always prefer more time. So yeah, then we will update the schedule and inform you via an announcement. about the Saturday session, but other things are the same. So you will have the next session on Wednesday, same time, and we will update you about the in-person workshop as well. Dhananjay?
Thank you, Viduranga, for that amazing session. Hope you all got a great understanding about the fundamentals of quantum computing. So before we wind up today's session, first let's take a group photograph. I'll send the background image via a link so that you can set it up. I've sent the link. Then let's take a group photo after setting up the background image. Yeah. Sorry. And with that, shall we take the group photo? Okay. Yeah. So I'll take the group photo. All right. Say cheese. 1, 2, 3. All right. Okay. We got the photo. All right. Thank you so much for joining with us today. We'll hope to see you there on next Wednesday, which is this Wednesday. Sorry. And yeah, thank you and have a good night.